Hello. Okay. Thanks a lot, John, for your kind introduction and for the opportunity to share our research or our study. As you have said, in Ingeniería Cero, we have been working for several years on wind, turbine, tower and foundation design. And during this process, we have came across some problems or decisions to be made based on the accuracy of the estimation of our foundation stiffness. So let's start with the index of the presentation. Okay, I will talk about the motivation of this study, the different sources of non-linearities in this study, the different methodologies we have, or present methodologies, both analytical and numerical. Then we'll go on an analysis case we have done for this presentation, in which we can see the influence of different factors like uplift, the footing stiffness, the influence of plastic strains, in which we'll present the study with some advanced soil constitutive models, cyclic loading, and structural nonlinearities. And after we'll go through some conclusions. Okay, to start with, let's talk about a little bit of the motivation of this webinar and study. Nowadays, there is an exponential growth in the provision of wind energy and the construction of wind farms in the recent years. Okay, this leads to an increase in demand of higher towers. Okay, here we have a graphic and we can see up to 205. We have towers of 150 meters. Now it has increased and we're reaching 150, even 160. Okay, so as the height of the towers grow, there is a higher influence of the foundation in the whole system, in the tower design. Why? Because the tower grows and also the shape of the foundations, so the flexibility of those foundations have more influence in the whole system design. And also, of course, we have to take into account the soil structure interaction. Okay, just a little note, when we start our tower and foundation design, the supplier gives us the Campbell diagram. In the Campbell diagram, we have the agent frequencies related to the excitations. We normally have the rotor speed, and we compare with the natural frequency of our tower. Okay, before we had the hard design in which the frequencies were over the resonance frequency of the rotor, but as the height of the towers have grown or have increased, we have gone into soft designs because we couldn't make so stiff towers. Okay, and also the margin we have in this estimation of natural frequencies from our structure is the plus minus 10%. Okay, so with such a small margin and such flexible towers, does our foundation stiffness estimation have that accuracy? We wonder and we make that question, because as it grows the influence of the foundation, are we near that 10%? How does our stiffness influence the accuracy of that frequency? Okay, so the aim of this webinar is to improve the prediction of the foundation stiffness estimation, to evaluate the influence of different nonlinearities, and our scope is a shallow foundation with a typical wind turbine foundation with circular shape and in drain conditions. Okay, let's have a look on the nonlinearities or the sources of nonlinearities we have when designing the foundation. we have structural and geotechnical nonlinearities. From the part of structural ones, we have the flexibility of the foundation and its stiffness. We can consider it rigid. Crack is normally in reinforced concrete, so we know that it cracks. And the geotechnical nonlinearities, we have nonlinear material and the uplift and soil plasticity, and also the cycling law that has some effects on our terrain. Okay, which methodologies we have or how we front that problem? Normally, we have the classical approach, which is an analytical expression, which is in the all guides and normative. The second group, we have done three methods: the analytical one, which are the classical, the second group, big group, in which we consider the 3D FEM models, and in it we have two subgroups. One in which we represent the terrain with the modulus of subgrade reaction, in which we represent it by spring elements, and the fully 3D FEM, in which we represent with solid elements, interface elements. We represent the interface between soil and structure, and in which can include all the nonlinearities, general shape of the foundations, construction process, etc. So let's have a quick look on the classical approach. Here we have an example of the DNVGL guide. It's based on analytical expression, and it's included in standards and guides. The variables we use to represent the foundation and the terrain is the equivalent dynamic shear modulus and the Gaussian radian, and of course, the foundation geometry. The pros that has this method is that it's very simple and fast, and you can have a direct measurement of soil parameter in order to determine the parameters you need to use the method. Okay, the cons it is for a rigid foundation. Okay, we know that a rigid foundation has a relationship between the depth and the dimension of the cantilever, if we call that, around 2. So it's valid or in the range of footings of 15 meters. But nowadays we are reaching 19, 20, 21 meters. So, okay, the other con it has is you consider an elastic soil behavior, and it doesn't consider the uplift of the foundation. So we can say that it has a lack of accuracy in big foundations. On the methods that use the modulus of subgrade reaction, okay, we introduce spring boundary elements which are based on that subgrade reaction modulus. We can either use shell or solid elements. The variable we introduce is the modulus of subgrade reaction and the foundation geometry. In these methods, we can include the stiffness of the foundation itself. The pros, it is that it considers the lifting, because we use gap elements or spring elements with a gap. It has nonlinear behavior. It has a low computational cost. On the cons, we have to obtain by correlations the subgrade reaction modulus. So we don't have the terrain represented by a direct parameter measurement. And also it has a scale, as it's based on correlations, we have the scale effects on the test, okay? So sometimes we need to calibrate that model. So if we need to calibrate the model, why not to use a fully 3D model? So let's go to the 3D model, okay? These models, we can see here the image, some with Diana, is based on finite element model with solid elements, with which we represent the terrain, also the foundation. We can see here in different colors all these elements, and we introduce an interface elements between the structure, the soil, and we model or simulate the soil with the constitutive laws. Here we have the variables we use, the soil strength parameters, the soil deformability parameters, and we also include the foundation deformability parameters. The pros of using this method is we can determine the parameters or define the parameters of the soil with the direct measure of soil parameter with testings. We can use it in all soil ranges. We can have a general foundation geometry, and we also can include the construction stages. Okay, the cons could be that it has more computational cost and you need more engineering hours to do it. Okay, what about the constitutive laws we can use in these 3D models? We can use Moore Coulomb, which, well, we can use a lot of it, but what we have used in this study are two different models. Moore Coulomb model, which is an elastic, perfectly plastic soil behavior model. We have here the graph which represents the behavior of the soil and the parameters we need to define it. The cons of using this soil model is that it has a constant load and reload modulus, as we can see in the graph. The modulus should be adjusted to the operational range you expect. As we know, in turbines, we have different ranges of loads, the initial ones, the maximal, the operational ones, and this soil model has a better adjust with some soils. Okay, there is another advanced soil model, which is a hardening soil small strain, which has nonlinear stress-strain relation. Here we have the graph in which it represents the behavior of the soil, and the cons we can say about this model is that you need more geotechnical testing in order to define the parameters. Okay, so here we have a matrix in we compare the three different methods with the different nonlinearities we believe that are important when designing a foundation. So we have the classical approach, which does not consider gap or uplift, not the foundation stiffness, nor the soil plasticity, nor cyclic loading. We have the modular subgrade reaction method, in which are FEM models, that considers the gap and uplift of the foundation stiffness, but doesn't consider soil plasticity nor cyclic loading. The fully 3D FEM models, and depending on the model of the soil, or the constitutive law of the soil, we have the Moore Coulomb and hardening soil small strain, in which we see that for Moore Coulomb doesn't include cycling loading because it has the same modulus for loading and reloading or unloading, and the hardening soil small strain that has all the nonlinearities included. Okay. Here, well, we have make a summary on a methodology comparison, the things that we have talked before. The pros for classical approach is simple and fast. You determine the parameters with the direct measurement, but it has a lack of accuracy in big foundations. With the subgrade reaction, we obtain by correlation the subgrade reaction modulus. So sometimes we need to calibrate the model, and the 3D model, which, well, we have the cons of the Moore Coulomb, but with the hardening soil small strains, we just have more time consuming. Okay, so let's move to the analysis case we have made. Okay, we have simulated a typical wind turbine foundation, circular one with 21 meters, and the material is reinforced concrete, and we have studied its behavior being infinite stiffness of the foundation, or the second, which is the elastic one. Okay. Now we study the different nonlinearities of different factors we believe with the different models. Okay, so what about the influence of the uplift of the foundation? Here in the graph we have the moment versus the rotational stiffness. The moment is in axis and the rotational stiffness. We have the line. We have a simple line, which is the determinant of the rotational stiffness with the analytical method. Okay, and now is compared with the subgrade reaction modulus method. Here we have that the blue one is that considering the rigid foundation, and the orange one is considering the flexibility of the foundation. So we have the second John modulus of the concrete. Okay, we can see here the decrease of the rotational stiffness. If we consider the gap or the uplift, it has a 15%. If we consider the foundation from rigid to flexible, we have a 20%, and in total, the comparison between using the analytical from the flexible and the nonlinear spring support base, we have 32% of error by determining that rotational stiffness. Okay. Here we have the same graph, but including the rotational stiffness obtained by a Moore Coulomb with the 3D fully method, and considering a Moore Coulomb with a hard soil and no phreatic level. Okay, so here are the yellow and the green one. So we have from the gap of 5%, the foundation stiffness of 37%, and a total of a 40% decrease in the rotational stiffness. Okay, by considering spring versus Moore Coulomb, we have a plus minus 10% difference. So what we are looking, or what we are observing here, is that the main importance is to consider, or one is much more important to consider, the footing stiffness than the gap on the uplift. Okay, so but what we can say is that with the analytical method, we are overestimating the rotational stiffness up to a 40%. Here we have some images with Ayana with the pressures in the footing. We can see the two first images, which are with infinite stiffness, so a rigid foundation and elastic foundation. We can see how the pressures on the soil change by considering the flexibility. Here we have, with the Moore Coulomb 3D fully FEM model, we have with the infinite of stiffness and with elastic footing. Okay. How does the plastic strength influence? Here we have included the plastification or plastic behavior of the soil by considering a medium soil. So this is the results. In the graph, we can see the results of fully 3D methods with a Moore Coulomb from a hard soil and medium soil, and with a rigid foundation or a flexible foundation. We have here the graphs, and the variation is by versus the analytical one. We have a 22% from the uplift, 30% from the foundation, and a total of 45% decrease of the rotational stiffness. If we compare versus, that was with the medium soil, with the hard soil, we have 5%, 37%, and a total of 40%. So we are around a 45 to 40 decrease in our rotational stiffness estimation. Okay, here we can see some images of the results obtained by Diana. We can see in the upper part of the slide the infinite stiffness footing. We can see how it maintains its plane, and on the for a medium and a hard soil, and with a flexible concrete, we can see how the flexibility and the deformation influencing the deformation of the system. Here we can see the evolution of the plastic strength in the terrain for a hard soil, for a medium soil. We can see that maybe the comparison between the values is not very high, but we can see how it propagates the plastic strength in the soil. And here a fully 3D model, but using advanced constitutive models, which is a hardening soil small strain. Okay, here in the graphs we have included the orange one is the model with spring elements, and okay, maybe you can see the one on the right side, which is a hardening soil. The blue one is the hardening soil with a hard terrain, and the green was the more Coulomb. Okay, we can see that in the beginnings for the moments, from low moments, the behavior is quite different, but from the service loads, which is the black line, vertical line, is the operational moment or the operational load we have there. It has a very similar behavior. Okay. Here we have with the advanced constitutive models, which is hardening soil small strain. We can see for a medium soil and for a hard soil. And we see qualitatively, we see the behavior that we have seen with the more Coulomb, but we see more the redistribution of the pressure on the terrain. Okay, so the difference between considering hardening soil small strain versus more Coulomb, why to use hardening soil small strain? Okay, the principal reason is because when we are designing a wind turbine, we have cycling loading, and that behavior cannot be predicted with the more Coulomb model. Okay, so we have introduced these loops of load in a model using hardening soil, small strain, and we have obtained that graph we have here, the comparing the moment versus the rotational stiffness, and we see how the behavior of the terrain influence that rotational stiffness. We have in red the initial or first loop. We have in the center moment without moment, so we load. We have the first upper part branch, then loading, where it puts loading, then we unload, we reload, and we unload. We can see how the slope and the different behavior of the soil depending on the branch of loading, unloading, and reloading. If we go to the second loop, which is in blue, we can see how the reloading has the reloading has different slope from the loading. Then we unload, we reload, and the third loop, we can see that almost are on the same load. Okay, so what's the point in this? That we have in a single model all the operational range, the initial, the service loads, and the maximals, and we can have all the soil layers. So we have a model which is independent of the operational range. Okay, but that's quite good because it seems that we have solved our problem. But now, how can we believe that? We can just say that it's true. Okay, so how accurately cyclic loading can be predicted? Okay, we have just get and say, okay, let's do a benchmark in order to know how accurately are we. We have taken a real large-scale test, which is documented in that document, large-scale load test and database of spread footings on sand from the Department of Transportation of the US, which is a foundation of shape 3 for 3 meters, and it has been loading according to that image. It has this soil layering, and we have made the same. We have reproduced and simulate that testing with Diana. We have introduced the same general soil layering, and we have load, reload, and make the cyclic loading they have done. So here we have the comparison between our simulation, which is in orange, and the real test they have done, which is in blue. So we can nearly say that we have a perfect match. So we can believe that model. Okay, let's move on another further advanced capacities. Okay, we have deal with the geotechnical non-linearities, and now we have the structural non-linearities. We have made, this is a model of just the foundation part, with the reinforcement. We can see in pink all the reinforcement and the solid elements which represent the concrete and the reinforcement. The model size, just the structural part, which is in the image, we have that solid elements nearly to 40,000 and bead reinforcement nearly to 24,000. No 60,000, and the features we have introduced is the total strain crack model, elastoplastic and bead reinfo, pretension anchor bars, and the interface tower bottom foundation. Okay, here we have another image, and we have the graph. We have the moment versus rotational stiffness, and we see the gray one with a hardening soil. Small strains, and for a hard soil. We have the blue is with non-structural linearities, no cracking of the concrete, and the gray is with the cracking. So we see that it's a difference between a 10%, so it's not so important for stiffness, but it has a remarkable influence in the rainfall quantities optimization. There are some studies that say that it can optimize, of course, depending on the footing and on the loads, up to a 20 or to 30%. Okay, which is normally in the cost of the wind turbines. It's 10% of the cost of the foundation is 10% of the whole structure. So it's quite. Okay, so just some conclusions. We can say that the flexibility of large foundation must be accounted for accurate rotational stiffness estimation, that nonlinear geotechnical effects play a significant role in stiffness determination, an approximate value that it depends on the wind turbine, the terrain, the loads, a 50% error in the total stiffness estimation from the footing leads to a 6% error in the natural frequency of the structure. So we can see it's not super critical, but we are reaching or approaching to the safety margin. Remember that we have said we have a 10%. And present computer capabilities allow for solving advanced geotechnical models in a reasonable time frame and avoid the use of subjective parameters. Use of nonlinear material models for concrete and steel improve stiffness estimation, but the main goal is achieving rainfall quantities optimization. And Diana allows the analysis of all foundation construction stages from early cracking risk analysis to ultimate limit capacity prediction. So for me, that's all. Thanks a lot for your attention. These three, but